here with me is Matanya Horowitz. Matanya is the founder and CEO of AMP Robotics, an AI robotics company that's trying to change the way we recycle using their pioneering waste sorting robots, including one robot that's actually called Sortie McSortface. Since founding the company in 2014, Matanya and AMP have been included in the Forbes AI 50 and in the Fast Company's World's Most Innovative Companies list. They also won the 2018 award for Top Tech Disruptor in the Circular Economy at the World Economic Forum in Davos. So happy to have you here with me. Welcome, Matanya.
It's so great to be here, Peter. Thanks for having me on the show. Here's my cheap joke. It's always great to talk trash.
All right, let's see what we can do.
Yeah.
Now, I'm going to dive in with maybe the opposite of talking trash. Congratulations. This year seems to be off to a great start for you and AMP Robotics. You recently raised $55 million B round. Yeah. What's that all about? What's going to happen?
Yeah. Well, so we've been, hard at work here at AMP, solving, as we see it, some of the primary challenges of the recycling business using robotics and artificial intelligence. And last year, I think we really got to a good inflection point for the company. We saw really widespread adoption of robots in the industry, really fantastic levels of performance from the technology. And went to raise a Series B to do a couple things. One was expand internationally. Another was to expand our product lineup. So as I'm sure we'll talk about, we use artificial intelligence for a number of different uses inside recycling, and we're finding so much that can be done. So the funding helps us continue to do that. And then we have some interesting new initiatives at the company where we are building what a very specific type of recycling facility called a secondary sort facility, and the funding also allowed us to really focus in on that and expand those facilities footprint.
So I'd love to dive into that secondary sort in a little bit. Now, one of the quotes from around your fundraise was that globally more than 200 billion worth of recyclable materials goes unrecovered annually. That's a large number, and I imagine that's only. I mean, the amount of materials used in the world is only growing. Hopefully, the amount that goes unrecovered maybe decreases
right.
over time. But that just seems like, I mean, how to even imagine that? What does it mean? 200 billion worth of recyclable materials. What does that look like?
Yeah, it's so. Stepping back a little bit, I think a lot of people look at recycling and they, maybe don't know much about it. They think it's done because of some sort of feel good, liberal something. Hey, is this stuff actually even recycled? And when you start to really dig into the industry, what you find is the industry really exists because of the value of all of this material. So there's good money in the plastics, the metals, the paper, and all of this, and they really do get reused. The challenge the industry has is that the cost of extraction, the cost of running this material through a recycling facility is really significant. And when commodity prices are low, can exceed the value of the material. So, I can pull out, $1 of cardboard, but if it costs me $1.10 to pull it out, you're probably not going to do it. It makes it a tough business. So, the thing that we're focused on is if we can reduce the cost of processing recyclables, there is so much value there that you can capture. You can sort of align all the incentives with material diversion. So, the challenge is there is over $200 billion, and you can do some quick back of the envelope numbers to back this up. How many tons of garbage are there? What fraction of them are plastics? What fractions are metals? And you end up with these staggering figures. The challenge is if you wanted to get it, it would cost over $200 billion to process that material. Right. And so what we're all about is if you can bring that cost of processing down and make it only cost $100 billion to get it, or $50 billion to get it, or even less, now recycling becomes this phenomenal business and you can really access all of that material value. And that's really exciting because all these economic incentives would line up behind it.
That's so interesting. And actually, a few weeks ago, we had on Mark Segura from ABB. And when we asked him about the kind of his vision for the future and how robotics could really make a big difference, he talked about essentially our current landfills as the future mines. And if robots were really, really smart, really capable, that's where effectively mining would be happening. Yeah.
Yeah. And, it's really, when we look at this, there's really two sides of the equation. There's what I just talked about, which is cost. If you bring the cost down, these things can be sort of very good ideas. And for landfills, what's interesting is a lot of older landfills are in sort of geographically good locations. And so if you can actually mine them and sort of reclaim some of the land, it ends up, you can get a lot of leverage or a lot of value even beyond just the sort of commodity value. There's another angle to it too, which is this $200 billion number is really premised. It's really, you're saying, I'm going to sell this material for about what the industry sells it for today. You can actually get a lot more value out of it if you can sort it to higher purities than the industry is capable of today. And in that case, that number can even look small. So there really is a lot of value out there just waiting to be captured if you can do it cheaply and do it well.
That's so interesting. And I must say, I know very little about recycling in our waste management industry. And so I'm really curious. I'm sitting at home where I live. There is essentially three bins we got. We got the greens and compostables. And I can kind of imagine what happens to that probably gets used for, I don't know, for farming or something to, help grow new produce somewhere. But then there's the landfill leftover, but then there's the recyclables, which is, I imagine, the one your company interacts with. It's the big blue container here. And I have no idea what happens after I put it in the bin. I often don't even know simple things like, if I'm not sure if something should go into the blue bin, and I'm not talking about something that would contaminate everything else, obviously, but just a box, should it go in or not go in? I don't even know if it's better to keep it out or it's better to put it in and they'll figure it out on their side. It's such a simple question. I don't even know the answer to.
Yeah. Well, so first, already, that's a much more sort of progressive and advanced recycling program. Most places don't have organics, in a separate bin that would just go to the landfill, which is especially unfortunate because that stuff can become pretty significant, greenhouse gas emissions because it eventually breaks down into methane and stuff. Even recycling programs, though, what's interesting is only roughly half of the United States has access to what's called a curbside recycling program. And so a lot of people don't even have that convenience, which means they don't really, recycle that much, typically. But yeah, so to tell you a little bit about how that recycling process works, all the stuff that goes in that blue bin, it gets transported over to a recycling facility and then gets dumped on what's called the tip floor, because these machines will literally tip the material out of them and just kind of fall on the floor. That then gets loaded into the recycling facility where you have all sorts of different pieces of equipment. A lot of it actually does look like mining equipment. So lots of conveyor belts, lots of things like trommels and different types of screens and stuff like this. And what those facilities are trying to do is use some sort of physical property of the material, like the density of it or its size or something, to kind of agitate it into one location or another. So one piece of equipment is called a disc screen. So you have all these spinning discs. And what happens is bottles fall through and then paper kind of floats over the top, kind of gets bounced over these discs. And that now you get a coarse separation between paper and plastic and other containers. There's magnets. There's something called an eddy current separator that's somewhat similar to a magnet, but it's for non-ferrous material. So non-magnetic material. So you have all these things and you kind of get all these different commodities separated into different spots. The challenge is that all of those machines are very sort of high throughput, but low accuracy. So you get paper with the plastic, you get plastic with the paper. And so you have tons of people, dozens of people in these facilities sorting out the stuff by hand and correcting those mistakes. Usually, to get back to your question, if you're unsure about what should be recycled, it's generally better not to put it in the recycling bin, because if the recycling facility isn't set up for it, that material can end up in the wrong spot and create contamination issues, even if it's fundamentally recyclable in some way. But yeah, it's confusing. Like, facilities are set up different, recycling programs are set up different. So even if it's recyclable, where you are, you could, drive 20 miles, into a different city, and it might not be recyclable there. So you get this really kind of like hodgepodge of different programs. So part of what we're trying to do is say, hey, don't worry about it. Like, the robots will take care of it on the backside.
Your robots actually will do different things when they're deployed in different places. It's not the same process they would follow.
That's exactly right. And so we'll have robots that are cleaning up the paper stream. They'll call that quality control. So because you're providing quality over for the paper, we'll do what's called positive sort. So the robots are picking plastic bottles of a particular type and all putting those in a spot. We also have robots actually in organics facilities where you do have a stream of that sort of green bin, and our robots are pulling out plastic bottles that aren't supposed to be there. But yeah, there's sort of kind of like 10 or so different niches in these facilities, and we can automate roughly 3/4 of them.
Wow. Now, before we dive deeper into that, I'm kind of curious. I imagine you didn't grow up and as a little kid were dreaming about recycling. What's the story? How do you end up, from who you were as a kid to now CEO of robotic automation for recycling?
It wasn't really a direct path. So yeah, recycling, I knew about recycling and I recycled growing up, but, like, my parents didn't even really care about it. They were sort of skeptical of the industry, I think. But for me, I was always interested in robotics and ideas around artificial intelligence. So I watched cartoons when I was a kid, and I loved Transformers and Ultron and stuff like this. And then when I went to undergrad, I started to learn about the DARPA Grand Challenge, which I'm sure you're familiar with, but there was a government program to have autonomous cars, race each other. And the first year they didn't work very well. But what I saw was, I at least had this feeling that robotics was a lot closer than most people felt back then. And so I thought, okay, maybe I could actually turn this into a career. So studied a lot of robotics stuff, went to Caltech to study for my PhD, worked with some great professors, but studied most closely under Joel Burdick, who did robotic grasping. And while I was there, this is around 2012, 2013, I saw a talk about this new stuff called deep learning. It was a presentation about like a specific algorithm around stacked autoencoders. So just kind of a specific particular niche of this. And I knew kind of how well computer vision was working at the time, but when I saw this, I got really excited. First, like the performance of these systems were, incredible, and you were starting to see human levels of performance. And then it had some really neat ideas about teaching these systems not just to identify stuff, but to kind of figure it out. So like it's like ideas like, if you want to identify someone's face, it's made out of two eyes and a mouth, and they have this positioning relative to each other. And I just thought that this was going to be transformational technology. So I wasn't doing any work in the area, kind of switched over and started studying it, and then looked for places where I thought it could be useful. I looked at different things in manufacturing and logistics and agriculture, but then started visiting recycling facilities. And what I saw was there was just a tremendous need for automation in these facilities. I would talk to people who were running the facilities, and I'd say, what do you think of robots? And I thought they would be skeptical. They'd be like, okay, here's someone from the public wants to talk about Wall-E. Like, I'm sure they run into that all the time. But instead they said, this industry absolutely needs robots. And so I just dove in and started to learn and talk to people, and then got the company going.
Yeah, so I'm curious. You started AMP Robotics in 2014, essentially right out of your PhD from Caltech. It's always So it's one, I would say it's the biggest adventure is starting a company. And it also takes a bit of a leap of, just jumping in and doing it. I'm curious, was there a moment where you just concluded this is just what I'm going to do?
Yeah, I think, it was probably earlier when I knew I had to do something with deep learning, because I just had this feeling that if this technology is going to be like this technology will be groundbreaking, and there's going to be a lot of potential, and so I somehow have to be involved. And I remember thinking, if the company didn't work out, at least I will have learned something, and if I was going to fail, it would probably fail really fast. So it actually seemed like a pretty low risk thing. I was also very fortunate to have a girlfriend. I think, or we were engaged at the time. Now, my wife, who she was willing to let me try it out, and so I was actually a little bit supported by her as well in the process to just as I was getting started. So that was a big part of the decision too, that mitigated risk. I was also fortunate to win a grant from the National Science Foundation through their SBIR program, which stands for Small Business Innovation Research. And so we did have some initial sort of very seed funding, like low level seed funding, and that also mitigated some of the risk as well. So I tried to position all the chess pieces as well, but if that hadn't worked out, I was going to try to find something else to do in deep learning.
Now I'm curious, when you started AMP, was it just you? Were there other people involved?
Yeah. So very early, actually, my brother Benjamin sort of mentored me, and so I was just coming out of grad school. I didn't know anything about business, and he'd been a programmer for a very long time, and so he encouraged me to kind of go for it. We did some coding together on different sort of simulations and things like that we thought would help prove viability of the concept. Once we got the grant, I was able to bring on two guys, James and Andrew, who helped write some of the initial code and get the first demos working and things like that. So absolutely, there was it wasn't just me. There was support from all these different people, and it was a huge part, of actually building some real momentum around this.
Now, when you get started, I mean, how do you even get started? You must have had some specific initial goals, something that you wanted to automate or partially automate. How did you choose that?
We were focused on this problem of manual sorting in these facilities. So I talked a little bit about how these facilities are set up, but a large part of the operation is people standing around conveyor belts, pulling out stuff by hand. And so it's the 3 Ds of robots. It's dirty, it's dangerous, but it's sort of worse than a lot of the typical dull, dirty, and dangerous jobs. This material is rotting, it doesn't smell good, you have old milk, there's tons of flies, because of how these facilities are set up. You have material that's being brought in, from the trucks, and so they have to have these big bay doors that let those trucks come in and out. And so you're basically exposed to the elements as well. So these facilities will get very cold and very hot. The result is very high rates of turnover. And these facilities are often run understaffed. If they have 20 spots, they'll hire 22 guys and hope that 18 show up. And it makes it very difficult to run a business. So the question could we automate this sorting problem, which is really just a picking problem? Like, people are looking at a belt, there's a bunch of stuff on it, you're trying to get all the bottles, or you're trying to get all the cans. And it really, when you look at it, especially as a robotics person, it kind of looks easy, right? There's a conveyor belt, the environment is, somewhat structured, you're only going to be picking in a certain area. And what I saw was that the problem was easy. What had been missing, the only reason people hadn't done this before, is because there was no vision system that could identify the material, because the material is inconsistent, it's smashed, it's folded, it's dirty. And so with deep learning, you now had such a vision system. And so it's this great pairing of this difficult problem people didn't want to do with sort of technology that now made it feasible to automate.
A couple of recycling facilities a few years ago, and I mean, everything you say really resonates. I would say, in addition, the thing that really stuck with me in terms of discomfort of being there was the noise. Like there was so much noise. I mean, because so many of these machines make so much noise that are shaking, and that's they're shaking on purpose. Normally when a machine is shaking, vibrating, you want to fix it, it's not supposed to. But they're violently shaking because that's how some things get separated. And so it's just part of the whole thing. So much noise. And also what I saw on the belt is like very sharp things on the belt. So, I mean, obviously workers wear protective gloves and so forth, but I mean, it just, but then I would say when I looked at it, my reaction maybe wasn't yours. You said, oh, maybe it should be easy, but my reaction was this is going to be very hard, because even though for humans, it might be easy if you stay focused, though the belt goes pretty fast, so you gotta keep up. As you say, everything's smashed, and to me that seems really hard to have an AI/vision system that can handle all this variation, because you never see the same situation twice. It's so unstructured. I mean, at the time, deep learning wasn't as good yet back in 2014 as it is today. I mean, was it already feasible at the time, or was it the whole process to kind of build up the system to become good enough?
Yeah, no, I definitely am being a little bit glib about it. There's multiple layers of difficulty in there. Just like you're saying, the grasping problem is really difficult. The stuff is smashed up. It's also all piled together, and so it's really hard to kind of get a good hold of things. And then, the inconsistency. The inconsistency is really hard in a couple of ways. It's not just the fact that it's smashed and folded and dirty, like that. That really is the core of it. But there's so many different types of packaging out there, and you have to have a good system. You have to deal with a huge fraction of it right up front, right? So you're, dealing with all these different types of plastics. One of the materials we started with was cartons, so milk cartons and juice cartons, and that was really hard to start with because they're boxy and they have a lot of similar graphics with things like cereal boxes and other boxes. And so, the vision system was using like, symbols and graphics and things like this, like logos, but those were shared across other items. And so there was a lot of confusion of the system between things. I think, and you're right. The deep learning was pretty nascent. So some of the first systems we made actually use support vector machines, which is sort of the technology that was before that. But I think we had this faith from seeing some of the early results for like like identifying cats in YouTube videos, like that paper that like it seemed like a similar problem. And so with enough data, we would be okay. Mm-hmm. So what we found was, there's a couple things that work to your advantage. Because it's so difficult, the industry actually has pretty loose standards on material quality. And so you don't, like if you look at a manufacturing environment, you really need to be like 99.9%, accurate or higher, actually much higher in most cases. In the recycling industry, a purity standard of kind of 90 or 95% is considered like, that's pretty good. And so that ends up giving you a lot of slop that you can use when making an initial system. That's kind of what we did, is we just kind of focused on a couple pieces of packaging and then just kind of kept adding to the data set. But like the initial versions of our system did not work very well. And actually we broke a lot of robots. And in terms of like some of the other things you brought up, like there are real hazards. People put hypodermic needles, knives, propane canisters in the recycling, and all of these things can hurt people. We had like bowling balls hitting the robots and stuff like that. And the biggest hazard for us, or for the robot, the thing that the robot buster was, it was stuff the robot actually should have like had to deal with. It would be milk jugs that were fully inflated with a cap on it. And if the robot hit it hard going too fast, that could blow up the robot. Also just boxes, like some boxes are so strong. You really don't think about it, but you could stand on one. Uh-huh. And so for these industrial robots, if they plow into it, you can break them really fast. And
part of that is, there's many different types of industrial robots. And when I watched the videos of your robots, there are these spider-like robots that are a bit different than the ones that lift cars, let's say. The ones that lift cars would probably not be troubled by a bowling ball all that much. So I'm kind of curious. I mean, I know a lot of your innovation, probably almost all of it is on the AI side, but how about the robots? How do you make the choice of going with these spider-like robots?
Yeah, I think they're the coolest looking robots. It reminds me of something out of the Matrix. So we actually started with a different style. We started with what are called Cartesian robots. They kind of move a bit like an Etch-a-Sketch, and we broke that robot, and we moved on to a Scara, so a little bit closer to a robot arm. We broke that, but we really wanted those to work because the idea was that those robots would be very compact, quick to install, and it would make the sort of sales process really easy. Like I could come in and put in a robot, in an hour, and then I'd say, hey, you can borrow it for a couple of days, and if you want to keep it, then you can start paying the robot. Mm-hmm. But what we found, was these hazards, and also kind of more niche problems, like a lot of the conveyor belts are cleated, meaning that they have sort of fingers or elevations on them to help the material move in a certain way. The robots, if they got jammed against these cleats, would get ripped apart. And so what we found was even these Scaras, the robot arms that were nominally supposed to be able to handle the environment, just the gearboxes would get worn down just from this repeated hammering against material and stuff. So we actually then moved on to this Delta style of robot, this kind of spider looking thing. And the reason was that all of the moving parts in those are contained up in the base. And then they have these really spindly arms that reach down to the items. And if something bad is going to happen to the robot, those spindly arms get broken or they pop off the robot, and those are cheap to repair. And so what we basically said was, if we're going to potentially bust robots, let's pick a robot where an issue is a $500 issue, not a $5,000 or $10,000 issue. And then that actually sped things up a lot. We didn't want these robots to break ever, but if they were breaking, the customers would have spare parts. We had spare parts, and they would pop a new arm on and be up and running in a couple of minutes. They're also some of the fastest robots you can get. And so we found from our customers, they really cared about the throughput of the systems. And so we found ourselves getting pushed in that direction.
That's so interesting. When you say throughput, how fast are you talking about?
So today, we've had robots run as much as, in these applications, kind of 120 picks a minute. In contrived settings, we can get up to 140. Most of our robots do between 80 and 100 now. So what I just said was kind of the higher end. And that ends up being comparable to roughly 2 people in these applications. So a person can do 40, or a person will average 40. They can do up to 60 or 80, but you'll find they get tired and kind of slowed back down to 40. But these are, pretty good speeds. We have a couple advantages in our application, which is the material's already damaged. So we can be super rough on this stuff. So when we come down on the material, we smash it, then we throw it. Nobody cares about their plastic bottle getting smashed one more time. So that's a big part of what allows us to get these high speeds.
It's so interesting. You've alluded to this a couple of times now. This notion that you can do a good enough job, a very valuable job with these robots, if they are pretty good. They don't need to be perfect the way you might expect. A car is built, a defect could be deadly, someone's driving it later.
Yes.
Here, these things are being recycled. They're going to go through a pretty rough process afterwards, I imagine, to be turned into new materials. And I wonder how it might affect your whole machine learning process. Can you say a bit about how you started training your vision models, and how this kind of deployment affects how you can improve them? Yeah,
it's a good question because it's tied closely to the sort of business strategy. So we were really a first mover in using robots in the industry. And what that meant was we had a lot of customers who were dealing with this pain point and were willing to cut us a lot of slack as long as they saw progress. And so we, back in 2015, 2016, the neural nets, the identification didn't really work that well. We were able to identify stuff, but the purities were kind of comparable to a person, maybe a little worse, maybe a little better. But even with that level of performance, we could essentially suck up all the early adopters And we found that we couldn't really get good levels of performance until we had data coming from multiple facilities. So our system could generalize across those multiple facilities. And so, it's interesting because as we see it, it allowed us to move quickly. People were accepting of the performance of the system as it was then. We ate up the early adopters. Now that's a bit of a barrier to entry for someone else. It's hard to get that first dozen facilities because if someone was willing to cut you the same slack they cut us, like we probably got them as customers. Uh-huh. But yeah, the other piece to the strategy was the idea that, hey, the system is doing today's performance is the worst performance it'll ever have going forward. And so it's really important that we have access to all of these systems. We can gather data and then provide software updates to our customers so they can benefit from the system's performance improvements over time. And that's what we've done. All of our systems are networked together, pooling their knowledge. And so systems that were just deployed 5 years ago, now they have exceptional accuracy and performance because they have the same neural networks as what's being deployed today in our new installs. But yeah, so it was really a question of like, how do you find the easiest problem to solve that can still solve a meaningful business problem, and then expand and try to aim for quality. The plan wasn't to sell a bunch of really badly performing robots. It was just like, hey, let's find where there's the most slack, and then we can create the fantastic system we know is possible.
So Matanya, I'm really curious how you get started on this. That the very, very first system, because I'm just imagining, you got to train off of something to start out with. Curious, did you set up a small recycling center of your own, or did you right away go into a real facility?
We did. I actually, I have some photos where I was dumpster diving on the weekend to get enough bottles and cans for our data set. It was actually kind of funny. We had this lab. It was really small. We basically had one conveyor belt, and that's where we would put the material and do the training. But it was in an office, sort of industrial office building. And we left all the material everywhere to go home for the night. And I got a call from the janitor, and he was really upset because he was like, I don't know what kind of party you threw, but like there's bottles and cans everywhere. And, don't do this again. And I was like, don't throw that out. Like it took us a couple of days to get all that. Don't clean it up. Like, it's fine. We don't mind the mess. And he was like, oh, okay. In that case, like, that's fine. And he got it. But he almost, recycled all of our data. So we had our own data set. We had a conveyor, and we were training on this stuff. What we found was in that controlled setting, consistent lighting, most importantly, you're running the same pieces of material again and again. You could create a really compelling demo. And then we would take some video from a real customer site, and we would see that it didn't work at all. So there was a real focus on getting real world data as fast as possible. We did things like we would go out to the customer sites and we would record data. So it was a laptop and the camera we use, and we would just sit out there and get like 5 hours of data, which was more than we could annotate, and try to get that. We just found that there was a huge need for a lot of data for that before it was going to work well. The customer site, the material was changing a lot. There would be lighting condition changes and things. But what we could do is we could create really compelling demos, have people stop by, and they would get excited, and that would get us sort of the goodwill to get into these facilities. But yeah, initially, we also pitched it in a certain way. When we put in the robots, we said, hey, look, it's going to take weeks before this thing is decent. Let's put it somewhere where it doesn't get in your way. And a lot of the recycling facility guys really understood that, and were willing to let us do a lot of annotation and things before expecting the robot to work well.
Now, I like the point you're making there about data collection. And these days, I feel like, if anything, a lot of the conversation about AI and deep learning has been heavily shifted towards the data and the process around the data, beyond just talking about, which exact neural net models are going to be best at extracting information from that data. So I'm curious if you're able to share anything about the AMP Robotics data process and how you go about it from collection to models that are trained and improved upon the previous ones.
One of the key elements is having a wide diversity of data. So all of our systems are set up. We have a VPN, a virtual private network that connects all of our systems to some cloud infrastructure we built in. Then we have a data annotation team. So dozens of people who are going through this data all the time and saying, hey, that's a bottle, that's a can, that's a piece of paper. For us, it's not just about quality. Like the quality or the performance of our system is quite good. We're getting more specific over time. So we're trying to teach the system new stuff. So as an example, we had a paper category, and then later on we split it into cardboard and other types of paper. And then within that, there's all these subtypes of paper you never would, care about unless you're in the industry, like newspaper, office paper, something called wet pack, cardstock, like all of this stuff. And so we're teaching the neural nets all these things, and the annotators spend a lot of their time on that sort of specificity. But that the people going through it are what creates our data set. So it is manually curated. And then we'll take the data set at a moment in time, and we'll run it through a training process. And we've played around with different training processes to find something that worked well in this industry. And that'll produce this neural network that can be downloaded by the systems and used for identification. Like you said, there's a real art to it. Like I think a lot of people have found, a high integrity data set is absolutely critical. So you really need your people to be making the right decisions. Mm-hmm. The material is so confusing, like it's all smashed and crumpled and all of this. And so if you're consistent, you say, okay, you tell it this bottle is a piece of paper, like it gets really confused. So a lot of focus is on having that high quality data set. And then, there's certain things we do that are sort of, I think, standard fare, like different types of data annotation and stuff like this that helps boost the performance. And we've kind of found the right recipe of stuff that works well. But then those networks get deployed and the systems get better over time. And sometimes we'll update we'll have updates about once every couple of weeks. Sometimes we'll have more often or a little less often, depending on what we're doing.
Now, if the system is trained to recognize what type of material is where, it also needs to know how to pick it up. Or, mm-hmm. I mean, maybe it's easier for recyclables than for, regular objects in warehouses, maybe. But at least in our experience in warehouses, it's not just about knowing where the object is. You also need to know exactly how to pick mm-hmm. it up, or you're just not going to get it.
Yeah. No, that's a huge, huge part of it, just like you're saying. So what we have done is focus really heavily on using pneumatics and vacuum to pick up stuff. Mm-hmm. And we found a lot of success in that, but there is a certain level that we're able to get to, which is for most materials, we have about 95% pick success. So mm-hmm. the robots will drop 1 out of 20 items. Now in the industry, that's considered good. Like, most equipment, they try to aim for a 90% recovery rate. But at least to me, it is the sort of primary performance deficiency of the systems. And a huge part of that is because we've used different sort of techniques that aren't machine learning based to try to select spots on these items, like trying to estimate the center of mass, or just going for the center of the object, or other things. And there's definitely more performance we can squeeze out by being smarter about what we pick. But most of our improvements have been around just making the gripper a higher flow and sort of redundant in different ways. But that's kind of a huge push, is to try to bring that up. If our robots get to 99% pick success, which I think would be a sort of a minimum bar for a lot of other applications, then a huge and then these robots are flying. Like, customers get really excited. You get excited about it at 95%, but it's a huge challenge because of different objects will naturally have a good spot to pick, but then when it's smashed up and things like that, you get all these folds, and it makes it even more difficult. And then when the object is partially occluded, it also makes it difficult. So we also sort of, again, kind of aim for like what was good enough. And for a lot of customers, actually 90% or even 85% was good enough. And that's kind of what we started deploying. But it's a frustration of mine because it's the biggest single performance deficiency we have.
What's the downstream process that makes it okay to be, let's say, 90% accurate, and that's good enough? And could anything change in the future in that downstream process when you're more precise? Yes. That would create a lot more value there, maybe.
Yeah, that's really the vision here, is to do exactly that. So the challenge the recycling industry has is because of this, the state of the art of the equipment, not speaking about ours, but other types of equipment can't deliver the purity that the buyers of that material want. And even if you can't do it reliably. So what happens is at every step in the supply chain in the recycling industry, the guy who's buying the material is cleaning up the stuff he just bought. And so there's a lot of sort of repeated sorting. It also means that because nobody knows the quality of what's being transacted, it trades at a discount compared to what it would really be worth if it was pure. And you see pretty big swings. So material could be sold for half of what it would be sold for if it was highly pure, over 99.5% pure. So yeah, the result is everybody's kind of just adjusted to this reality because no one's been able to do better. If you can produce pure material at the beginning and you know that the rest of the supply chain isn't going to have to adapt to it, it allows you to have all these efficiency gains. Not every part of the process needs a sorting system, but it also lets you, what part of our hypothesis is that the technology that you use inside of paper mills or what are called plastics reclaimers that melt down this material and use it can become much simpler if they're able to accept pure material. Just to talk about a little bit more, what you find is you basically have different uses for the material depending on how pure you get. So PET bottles, so number one plastics like Pepsi bottles and Gatorade bottles, most of that becomes textiles. So they become clothes. I'm wearing a recycled PET shirt, and it's worth something. It's good. But if you create highly pure stuff, it can become food grade PET, which is what can be used for bottles again. And the demand for that is much higher. And so, yeah, if you produce a 90%, 95% pure PET bale, it's going to probably become textiles, but also carpet. If you get 99%, it might go back into being a Pepsi bottle again. And that's what everybody wants to do, is sort of this full closed loop recycling. And so, yeah, huge benefits. Yeah, it's actually incredible to think about. So this $200 billion number that we talked about, it's not assuming you have some of these upgrades to material value. And if you did, that the pie becomes much bigger. And that's what we want to do.
When you talk about these different steps downstream, I can't help but think that maybe right now, some of your robots are sorting in one facility, that gets packaged up, gets delivered to another facility, and maybe there are some other robots of yours.
Yes. Yep. Yeah. So we, because the sorting problem is sort of ubiquitous in the industry, we will be at multiple steps of the supply chain. So you sort of have the consumers and businesses, and they're producing material. You have haulers who bring it to recycling facilities or landfills. After the recycling facilities, you have three main entity types that are buying these commodities. One's called plastics reclaimers. So they'll melt and shred down the material and turn it into pellet that can be used in injection molding machines and stuff like this. You have paper mills, and then you have metal smelters, so aluminum smelters and things like that. So most of our customers are the recycling facilities, but yeah, the plastics reclaimers, paper mills, and things like this are also customers of ours. And our robots are producing material that should be purer than is typical in the industry, so it needs less sorting. But actually, it'd be an interesting question. I'd say, let's say our robots are cleaning 2% of the material stream in the United States today. When we're at a plastics reclaimer, we're still cleaning up the rest of the material from all these other sites too.
We are dropping new interviews every week, so subscribe to The Robot Brains on whichever platform you listen to your podcasts. In your announcement for your B round earlier this year, you mentioned something that you'll also get into secondary sort. Mm-hmm. What is secondary sort?
So here's an interesting opportunity. All these recycling facilities are creating low quality stuff. If you had higher quality stuff, you could sell it for a lot more. Mm-hmm. You kind of see the opportunity there, which is the industry has an inefficiency around quality where you could see a new type of entity that buys material from recycling facilities, sorts it again, and then sells it on to the reclaimers at very high quality. And that's what they call a secondary sort facility. So you're sorting a second time. And with the artificial intelligence technology, with the robots, we can sort to very high qualities when the facilities are set up, when we control the facilities and we kind of set the facilities up to be optimized for our technology. So for our robots, a big part of why we deploy robots is they can be installed with almost no retrofit into those existing facilities. We basically bolt them onto the conveyor belts that they already have. And that works great. But really what we're doing is we're helping them deal with the challenges around manual sorting. And their overall process doesn't change. That's part of the pitch. We don't want you to change your process to take advantage of the tech. Mm-hmm. But if you say, okay, can I build, what do you do different when you build a whole facility from the ground up? Then it starts to look very different from what a conventional recycling facility looks like. And there's a lot of benefits you can have. You can use our vision systems all over the place and identify when material quality standards aren't being met. You can have a lot of redundancy with a lot of robots, right? Like, an obvious thing is putting one system back to back. Now you have 95% on 95% on 95%, then you hit whatever quality you want. And so, we've started doing this and building up our own facilities for the secondary sort. A very key part of this is because we choose what those facilities will buy, we get to control the feedstock, so we can optimize the technology for that. They're non-competitive with our existing customer base because we're buying material from them and serving as an outlet for them. And it's all kind of coming together quite well. So we already have one facility operating. We'll soon have our second. The interesting thing is that others in the industry have tried this before. So over the last kind of 5 or 10 years, several companies have started around the idea. The idea isn't new, but they've failed. Sometimes in really spectacular ways. And we think we are different because we control the full technology stack. So, if the performance isn't good, I get upset and I've run over to the facility and I can look at the code and figure out what's wrong. But as the whole team is, doing continuously, and but then also artificial intelligence gives you a certain flexibility with the technology that prior versions of these facilities didn't have. But the whole point is basically just to upgrade that material and solve this sort of supply chain quality issue for the industry.
Now, when you said some companies have tried this before and have failed in spectacular ways, I'm curious, can you give a bit more color to that?
Yeah, that might be a bit of an exaggeration, but they just went bankrupt, lost their investors' money. And it would be, it actually has been a bit of a challenge for us because we're going out into the industry and saying, hey, we want to buy your material. And by the way, we'll buy your lowest quality material because we think we can upgrade it efficiently. Uh-huh. And a lot of people say, that sounds great. But actually, I was already dealing with these guys and they said the same thing, 4 years ago. And when they went out of business, it was a huge hassle because now I had all this material I couldn't sell and stuff like that. Mm-hmm. Basically they, different entities set up facilities, spent millions of dollars or tens of millions of dollars, got everything running, got supply figured out, and then went out of business. And then these facilities get sold for pennies on the dollar sort of thing. And and the blowouts were sort of really public within the industry. The challenges is these facilities basically bet on different material streams. So they would bet on the value of a certain resin of plastic or something like that. And the recycling industry is this commodity market where these prices are changing all the time. And so when the market moved against these guys, they just got killed because they were sort of trying to sit as this middleman, and they can only sort of exist in this sort of band of value that they're creating by upgrading the material value. And so when commodity markets go down, that band shrinks. So for us, part of the reason we think we can succeed is the AI identifies pretty much everything in the material stream. So we can use these facilities not to just sort a specific type of plastic, although that's what we're focused on right now. We can separate out metals, we can separate out papers. And so we have a bit of a wider commodity basket that we can optimize against, and that diversity of applications that AI enables gives us more security in the economics for these facilities.
And once you do the secondary sort, am I understanding this correctly, that you could potentially achieve kind of the full recycling as you talked about, where materials get reused in their original use rather than a downgraded use?
Yeah, absolutely. And I will say, not just, but we're not the only ones that do that. Some entities in the industry can create high enough qualities that's already happening, and creating, food grade materials again. But absolutely, we want to significantly increase the supply of high quality material that's available for these types of in the industry, we call them end markets, but these types of uses.
Now, I'm curious. Obviously, you've deployed a wide range of robots. I think mostly in North America so far. Is that right?
Yeah, mostly North America. We do have some in Japan and Western Europe now, but yeah, almost all of them are here in the US.
So if I wanted to go visit one, are there any places I could just kind of go see your robots in action?
Yeah. So different facilities will have sort of public tours or not, but we have one up in Napa. I'm sorry, we have two over in Napa now. And the recycling facility there has been a great partner. We have some that are possibly closer, but I think we're still under NDA. Depending on where we are, we have some on the East Coast. We have one in every facility here in Colorado. But yeah, they're all over the place. Yeah.
Well, sounds like an extra reason for me to go to Napa.
Yes. Yeah,
not just go wine tasting, but also go check out your robots.
Yeah, I would suggest it after the wine tasting. The robots have a great view over from this recycling facility, but it's right next to a composting yard, so it's a bit it's not quite the same as a vineyard. Yeah.
Uh-huh.
Yeah.
One thing I'm kind of curious about is how do you count how much work or how much recycling your robots have done so far?
Yeah, we think about it in terms of the pick count. So we'll we have metrics that are automatically gathered, but robots doing 80 picks per minute or whatever, and then depending on the metric you're after, we may say something like if you care about tonnage or GHG emission reductions, we'll say, okay, the average milk jug weighs X, and so this many picks corresponds roughly to this much milk jug, which is natural HDPE number 2 plastics, and you can sort of extrapolate on that. But in a lot of cases, they are estimates based on this pick count number, which we do have measurements of. That's
interesting. That reminds me of when a while back I walked into the lobby of Tesla in Palo Alto. The offices there. I'm not sure if you've been there, but when you walk in, first thing you see in the lobby is a bunch of computer screens. And they essentially say, this many gallons of fuel saved with Teslas around the world, this many, supercharger stations and so forth. And it has all these kind of statistics. And I believe they live update even, I don't know how frequently, but they update to give you a sense of, what's been achieved. Do you have a similar dashboard for yourself or maybe even publicly?
We do. So yeah, if you walk into our lobby, it's I haven't been there, and I'm certain it's a little less visually impressive, but we have a TV and we stream live stats on there, and I think it's like how many picks done this quarter, and then the lifetime, like total picks over the lifetime and stuff like this. And then we have a sort of platform we've made, a web platform called Clarity, where you can log in and see these stats for different systems that are out in the field. I don't have the figures in front of me right now, but that's something we really like, and so it's very cool for guests to kind of come in and see those things, and then it updates I think once a minute or something like that.
Now it's still the early days, at least as far as I can tell in the journey. You have a lot of robots out there, but you not everything's being recycled yet, right? So clearly we're still in the very early days, and I'm kind of curious, how do you see this grow and expand in the next few years?
We are in the very early days. Now, there are some really interesting things happening in terms of people are much more aware of plastics in the ocean and greenhouse gas emissions and stuff. And so there's a huge push actually by brands and manufacturers to use more recycled content in their material because they want to be seen as, helping, move the world forward. But with our secondary facilities, with the robots, we're trying, like I said earlier, to basically collapse the CapEx necessary and also the operating costs of running a recycling facility so that more facilities can be built. A huge part of why so few plastics are being sorted is a lack of access to curbside programs. So people, maybe in half the country have to bring their material to a drop-off location, and that's such a pain that most people don't do it. Mm-hmm. But also, there's large sets of plastic types that aren't really recycled, and a huge part of the reason is it's costly to sort it out. Like, the technology doesn't exist and things like that. And so if we can make it easier to separate that stuff out, you'd start to see more uses of that. There's so many different examples I can give of these different things. But at a high level, yeah, the fundamental belief is you collapse the cost of doing this. There's enough value that it should become the dominant way waste management is dealt with. And not just here in the United States or in Europe, but all over the world. If you look at places in Africa and Southeast Asia, they don't have a lot of waste management infrastructure. And a lot of the plastics in the ocean problem actually isn't because of the United States or Europe. It's because of a lack of infrastructure in Southeast Asia. And so people are throwing garbage in the rivers and stuff like this. Some pretty sad stuff. If you can create incentives in those places to recycling, then you start to really go after these problems, and we think that's absolutely possible.
When I think about what you described so far, it's a robot system that is powered by AI, deep learning, to actually understand the material flow and understand how to pick and sort. That is a very specific aspect of recycling. And I'm curious, are there other things you see, maybe that you're taking on yourself, or maybe, are there maybe some really fascinating challenges that maybe are beyond today's AI's capabilities, but you say, hey, if somebody out there wants to really make a dent into this is really hard, but if you can make it work, it'd be really impactful.
Yeah. So I mean, we definitely think basically sorting as a problem is a huge bottleneck in the industry. And what AI has done is it's basically given us a low cost sensor that lets us sense things, and then you can use all sorts of things. We're working on technologies that are also non-robotic for sorting, not in terms of robot arms, but other things that use air and paddles to separate things and a bunch of other stuff. But so the mechanism for physical separation is only kind of one part of it. But yeah, that isn't the whole story. There is the challenge of what we would call them end markets. But if you separate the stuff out, is someone going to have a viable business turning that into some kind of good? And so in the case of the common plastic types, like number 1 plastics, number 2 plastics, there's an existing market that exists. Mm-hmm. An existing technology to process it. But there are some really exciting things happening around things like pyrolysis. So pyrolysis is a very specific chemical process that can kind of take a soup of stuff and break it back into more or less things that look like oil or other precursors that can be used back into making other plastics or other materials. That's important because depending on the generality of that technology, you can take a whole bunch of different types of materials and get a use out of them. So yeah, so pyrolysis is kind of one main name for this technology. There's sort of a broader class of this that kind of goes under the name advanced recycling. But more or less, there needs to be a use for everything in the garbage stream. Mm-hmm. I'm focused on plastics and paper because that's where a lot of the value is. But you really want to make sure, is there a high value use for glass? I mean, there is, but depending on how glass is kind of mixed up with other stuff, it can be degraded in different ways. If you can deal with those contaminants and create more value out of glass, that's important. Same goes for organics, things like tires, other materials, other metals that other recyclers don't want to take. A lot of this comes down to chemistry and material science, but also some clever industrial design to use all these materials. And what we're trying to do is say, hey, we can separate out anything at industrial volumes, and then we're in many cases, that's all we need. But for some of these materials, we're counting on that catalyzing a market for the materials. But yeah, if people wanted to move the recycling industry forward, I mean, of course, at AMP we're hiring for all sorts of stuff and focused on the sorting problem, but finding those different end uses and creating markets around them is absolutely huge and drives the economics of the industry.
Now, Matanya, if you think about the deployments that you've done so far, is there any one that stands out and about which you can say a bit more concretely about, what does it look like when you go install the system, and how does it ramp up over time?
Yeah. Well, so it's gotten better and better. I think, if you looked at the installation of the robot in this facility in Napa, we basically fully build the robot in our office and then ship it, and basically a crane just dropped it in, and it was ready to work, the next morning.
Wow.
But yeah, it for us at this point, it really depends on how much of the material we've seen. So if we're sorting the main plastic types, the number one plastics and number twos, the robot basically works out of the box. The neural networks are generalized enough that they can identify the stuff in new places. If we're doing something new, like our project in organics, or a different material stream is called construction and demolition material. So it's like wood and rebar and drywall and stuff like this. The system doesn't work that well out of the box, and we have to gather a lot of data. And so we'll focus our data team on that data from that site. And we talk it through with the customer and say, hey, we think, we're estimating here, but we think it'll take us 3 weeks, 4 weeks to get the system to good levels of performance. But yeah, there's two challenges there. It's getting the neural net up to speed if it's not already, and then the physical installation of the robot, which usually we try to basically plop in with a crane. And if we can't do that, we may have to take the whole thing apart and assemble it on site, which is possible, but it takes a long time, and it's hard work. Some of the components of the system can weigh 500 or 800 pounds.
Curious about this construction demolition. That's very different from everything we've talked about so far. So tell me a bit more about that. How do you get into that? And does that get transferred to a facility the same way?
Yeah. There's basically specialized recycling facilities just for this stuff. And, when people are demolishing a building or building up a house or something like that, they'll throw all this material in a roll-off or a dumpster. And that might be brought to one of these facilities, or it may just go straight to a landfill. But if it's one of these facilities, it'll get on conveyor belts, somewhat similar to the other ones, and people will hand sort out the wood. They'll try to get all the wood in one spot, all the drywall in one spot, plastics in another spot. So the material tends to be much bigger and heavier. We've taken our robots and focused them on sort of materials that are 18 inches and smaller, so smaller pieces of wood that have got mashed up in different ways, and then leave the rest of it to their manual sorters and other technology. So for a typical single stream recycling facility, we can automate 75% of the stations. In a construction and demolition facility, we can automate more like 25%. It's not as big of a push of ours because there's so much that's still possible in single stream, but we've branched out and done that. We've also branched into electronic waste. And so your electronics, if they're going to be recycled, people will take out the batteries and they'll take out the light bulbs in screens, and then they'll send it through a shredder, and you'll get little pieces of printed circuit boards and metal and stuff like that. And our robots will sort that. We've also looked at another segment, which is automotive shred. So shredded cars. We don't have any robots deployed in that, but it's yet another spot where robots can be potentially useful.
So interesting. In electronics recycling, I imagine if you can do it well, there's a lot of value because the materials, like I guess copper, potentially gold at times, are highly valued. Is it possible to actually separate those out?
It is actually, and this is one of the interesting things about the use of artificial intelligence in the industry is, so the industry has some other tools that they use. They use hyperspectral cameras, X-ray cameras to distinguish different plastic resins and things like this. It ends up AI just in the visual spectrum can identify stuff that those systems can't, not because it can see differently, but because of some other physical property. So what I mean by that is when the material is shredded or broken up, depending on the alloy, it'll actually bend differently. And the vision system can use those visual features to distinguish it. So there was some alloy of magnesium and aluminum for automotive shred. And the industry really wants to separate the stuff out. No technology does it well. And if you and me look at it, it's just like they're two gray pieces of metal. I couldn't tell the difference. But the system could, and we found it was because the magnesium broke in a certain way, and so it had a certain fractured pattern. And yeah, the AI picks up on that stuff. But there is a lot of value in this stuff. Electronic waste is sort of its own niche. We've worked with different recyclers who sort this stuff. It's interesting. A lot of the value they get is from being paid to take the material and then certified destruction. So for like sort of data integrity things, and then the material value can be actually a smaller part of the revenue stream for them than just showing that they destroyed things and dispose of them properly. It can be a good business. We haven't made a bigger push into it. There's a lot of environmental compliance issues when you shred this stuff. There's a lot of like hazardous dusts and stuff like that. Huge risk of battery fires and stuff. And so those recycling facilities, even though the material can be lucrative, they have a bunch of kind of costs associated with being run too. But there's some really exciting work being done by groups like more established players like ERI, which is one of our customers, and then also groups like Redwood Materials that are kind of newer players on the scene.
Oh, all super interesting. Now, Matanya, you're an entrepreneur. You're CEO, founder of the company AMP Robotics. And I'm kind of curious, do you have any kind of lessons or advice for other people who, maybe out of their PhD or out of their current job or maybe out of undergrad, also want to start a company?
Yeah, a couple thoughts. One is that it's in some ways a lot more rewarding than you expect. Like when you solve meaningful business problems for people, it's, you do it to build a business, but like you really do it kind of out of this, when you have customers, you really build a strong relationship with them. And then you find it very rewarding when you're solving things that have been headaches for them for a long time or keeps their business from really being viable or thriving. So I think people who get into it, you'll find in some ways you enjoy it more than you expect. It is a lot harder than I thought it would be. I remember thinking as soon as I got the robot running, the island in Tahiti would be, just a couple more months away. That was actually the easiest part of the whole thing. Building a team, negotiating strategic deals, like all of this ends up being much harder and taking a lot of thought. I used to do a lot of work in MATLAB and Mathematica and C++. Now I just work in Excel spreadsheets and emails, and I find it but in a lot of ways a lot harder. The other thing I would say for people that may not be obvious is it's actually a lot lower risk than I think people think, like at a personal level. People respect businesses will respect people who've tried something out. And so if you try and it doesn't really work out, at least if you're in a high tech field like robotics or AI or something like that, you're going to be able to find things to do afterwards. And there is a lot of funding for good ideas. And so, when you get the right investors and stuff like that, they'll really help support you and the business. And so, it just ends up being a lot lower risk than I think people think. But at the same time, you have to be willing to put in the hard work to find a meaningful problem that people care about. This
has just been an amazing conversation. I learned so much about recycling and just, this short conversation here with you. And I'm really thankful. And I'm super impressed with everything you're able to make happen and make our world hopefully a much better place as you continue to grow AMP Robotics.
Thank you, Peter, for the kind words. And I really enjoyed the conversation.